Delay-tolerant network on the railways. In the article, we analyze scenario when trains are moving on the railroads and may be in and out of the coverage of terrestrial radio network, mobile network, and trains can interact with each other. Out of the coverage, one train can send messages to the other train, which arrives in the coverage area faster. Thus, messages from trains to outer network can be delivered in such delay-tolerant network (DTN) faster with the help of other trains. Firstly, we analyzed a simple scenario when two trains generate one message. One train moves from city A to city B, and the other train moves from city B to city A, and these two trains meet. Coverage of automobile network is present only in cities A and B. If the message was generated before the meeting, then the message is transmitted to the train which arrives in the coverage area faster. Calculations show that if trains have the same speed, then maximum gain in reducing average message delivery time is about 12%. If trains move with different speeds, then maximum average gain can be up to 50%. Obviously, coverage area percentage and number of train meetings depend on population density in the region. In European part of Russia, most of the railroads are covered with mobile networks. There are a lot of trains and they meet very often. But these meetings occur inside the coverage areas. While closer to Siberia, trains more often meet out of the coverage. We analyzed railroad schedule and network coverage in one region which has population density close to average population density in Russia. This is Tyumen region. As we can see from the figure, a single meeting in one out of coverage zone is prevailing scenario. So DTN gain within 10–50% may be a good estimation of efficiency of the network in reducing message delivery time. To estimate efficiency of delay-tolerant network in general case, we made a generator of random railroad maps with random train schedules. Single meeting with single message is a very simple case. When passengers on trains generate a lot of messages out of the coverage or trains collect a lot of telemetry data, the problem arises that the interaction time during one meeting of two trains is insufficient for them to exchange all the generated or accumulated data, and time when a train is in the coverage area is insufficient to upload all the accumulated data. When two trains meet, they need to decide which train will appear in coverage zone faster. This train will receive accumulated data from the other train. Some decision-making algorithms are used. One of the simplest algorithms is an epidemic protocol. During meeting, trains exchange all the accumulated data and sender transmits all the data that receiver yet doesn't have. When data rates become insufficient for epidemic propagation of accumulated data during trains interaction, we need to use more sophisticated DTN protocols to maximize gain of the network. There are many existing DTN protocols, and some of them may be applied on the railroad scenario. When trains move according to a more or less strict schedule, earliest direct delivery or EDD protocol may be used. Trains simply decide who will appear in coverage faster. Or earliest delivery (ED) protocol may be used. Trains take into account the future meetings of these two trains in this protocol. DTN efficiency in reducing message delivery time and utility of accumulated telemetry is depending on ratio between network data rate and data generation rate. In faster network, we can get more gain, as it can be seen from the tables. In general, efficiency of DTN is more than 10% and may be up to 30–40%. Then we analyzed a real section of railroad in central Russia between cities Tyumen and Surgut. There are 11 pairs of trains on this section, 22 trains overall each day. We have a real schedule and we have a real coverage of three networks of three major carriers. We analyze network as total of three carriers and separate networks provided by one each carrier. We noticed that despite this railroad section has far not full coverage, trains spend a lot of time inside the coverage areas, as they spend a lot of time on stations and in the cities which are inside the coverage. So the efficiency of DTN is not so big as expected. We analyze the model in which passengers on trains exchange messages with people in the outer network, and we use two models. In first model, we use DTN only for uplink. In second model, we use DTN both for uplink and downlink. You can see two corresponding curves on the figure. Message delivery time is less in DTN compared to direct delivery without DTN. Thus, more messages in general are sent by a passenger in DTN. The gain is not so big, it is about 10–15%. What is interesting, we got more gain in DTN in reducing maximum message delivery time. Reduce of maximum message delivery time was within 15–25% of direct delivery without DTN. This may be crucial for some telemetry applications when information becomes useless after some period of time. Some of the trains may be equipped with satellite terminals. In this case, in rural areas out of terrestrial network, these trains may act as moving coverage zones. For common trains without satellite connection, these special trains extend and complement coverage area of terrestrial network, making delivery of messages faster. Average delivery time and maximum delivery time become lower. Next, we analyzed a railroad section between two big cities, Moscow and St. Petersburg. Nowadays, that railroad section is fully covered by mobile network, but in future that network may become insufficient as messages get bigger and someday a new network, for example 5G, may arise on this part of railroad. This network will start growing from the cities and big stations. In this case, DTN on this railroad section is very useful, as here we have more than 500 trains with lots of meetings. DTN potential while migrating to new network is big, as it can be seen from the figure. Maximum gain in DTN efficiency is achieved with low coverage of the network, so DTN is efficient from the very emerging of the new network. We recognize that potential of delay-tolerant network is determined mostly by train schedule, the number of trains and the number of their meetings. The less is coverage of mobile network, the more efficient may be delay-tolerant network in the part of reducing message delivery time or faster delivery of telemetry. So, DTN is more useful on the initial stage of network implementation, or during migration time from previous to new network.